So we had this balloon car from part one. We let it go and it traveled a certain distance. We measured the distance and the time. Then we modeled that with a quadratic equation with values for initial velocity and acceleration. We modeled it again with an exponential equation, values for A and for B. And then we modeled it with another exponential equation, tweaking our values for A and B. Do any of them work? Well, let's find out with data. We have a car, we have a track, we have a big screen there to take some good data. And don't make fun of my balloon car because it didn't go very far. The real data went a little bit further than this. It went about 20 centimeters, not 15 like it's shown here. But I needed to have it close enough to the motion sensor in order to take good data. And there it is. Specifically this part. And that part for the velocity. Yeah, there's some static over here, but we've got some good distance versus time data, and the first thing I'm going to do is put that data into a spreadsheet so I can flip it around. It just means that we're going away from the motion detector instead of towards it. All right, let's use the spreadsheet to draw our graph. Looks good, but it could also look like this. These two graphs show the same data, or they show different windows of different parts of the same data. And I'd say the top graph looks maybe a little bit better, more accurate to me, but I just know that doing experiments like this with students year after year, a lot of times the students will watch the car, come to a stop, and then say, okay, is it stopped? Click with the stopwatch. So sometimes there will be an extra second or two, and you might say that I'm exaggerating, giving 2 extra seconds of dead time there, but anyway, there it is. These are two views of the data. This was the data given to me by the data collection software. These are two views of it. And this is what I got with Model 1. Not very good. Same idea, not very good. This is Model 2. This is Model 3. Woof. These aren't any good. Let's try with the longer time here. Model 1. A little bit better there. Model 2. Model 3. What's going on here? Specifically, what's going on here at the beginning of our graph? Looks like we have something. We have a smiley face there. It's curved up there and then curved down for the second part of the graph. Why is that? Well, it makes sense. You release the balloon and then it's speeding up and then it's slowing down, speeding up and then slowing down. All three of our models are better with the slowing down part. Good thing it speeds up for only a short amount of time. Let's zoom in here and take a closer look. Well, this is kind of silly. It's curving up there, but it's silly because the data I clipped out has it going in the wrong direction to start. Let's get rid of that, move that over, and redraw our graphs. Take 2 with Model 1. Oh, that looks much better now. Just had to clip off that useless data there. That's Model 1, and we can quantify how well this model fits the data with the root mean squared deviation. A complex looking equation. It's really not that bad. Let's put it up there. N is the number of data points, x sub I is the observation, and x with the hat on it is the estimated based on your equation. What I'm trying to say is we'll take these two data points and take the difference and then square that difference, and then take the next data point, take the difference between what the data was and what my model said the data should have been, and then square that and then add that to the next one and divide by n and get a value. And there it is, and it's pretty small. And if you would like it to be 0, it's not 0, but there it is. And it's smaller here than it is for Model 2 or for Model 3, because our quadratic model fit better than the exponentials for this data. What if we had a longer time window there? Then what would we have with the RSMD values there? And I kind of like this. It's not great. It's not as good as the quadratic, but I think this is, it overshoots it, it undershoots it. But maybe we can make it even better. Again, let's take a look at our beginnings here. And you see what I'm doing. We have data. We have a model. We want them to meet up. So we're tweaking the model, but we're also tweaking the data. Now, I'm not lying about any of this data, but I did select a short race to get data that I thought would be usable. I am selecting the window that I want to look at, so I am making choices with my data. See what I'm saying? Don't ask me, can you model this motion with that behavior? Of course you can if you're willing to squint hard enough. Anyway, zooming in. I feel bad about doing this, but it's a smiley face. It kind of curves up there. And can we, yeah. Okay, let's take a look at it now. Even better. That's Model 1. Model 2, Model 3, still not great. Extend the time window 2 more seconds. That's the first model, the quadratic. There's the second model, and the third model, the exponential, outperforms the quadratic in this case. Hooray for that. But I can do you one better. Our exponential equation looked like this, and we had two different ways of calculating b. A was just the distance. But that's not necessarily the best we can do in terms of root mean square deviation. Look at this. The data collection software will write out an equation. It'll do a curve fit for you and give you a really small root mean square error. So there's our value, our new value for A, our new value for B, which they call C, and oh, there's another value too, B, that pushes the line up or down, and that looks pretty good. That's the lowest value we've seen until we do a curve fit with the quadratic. So I gotta say, and we're adjusting the windows to be ideal here, that the quadratic wins depending on what window you look through.